Hello guys, can you hear me? Please response. Okay, thank you. So let's discuss the assignment fourth. Here we will discuss PN junction. Okay. So see the first question. A PN junction is formed by joining. There are four options: two N-type semiconductor, two P-type semiconductor, P-type and N-type semiconductor, and metal and semiconductor. According to you, which option will be correct? Okay. So PN junction, only PN junction, P and N. As its name is also suggested, P-type and N-type junction is formed by P-type and N-type semiconductor. Please don't confuse. Just silly question. We have, let's say, P-type and N-type. When we join these together, let's say like that, this is PN. Here is a PN junction form. This region, depletion region or PN junction. Do you know P-type has majority? N-type majority is holes, whereas electrons majority charge carriers. So let me give you brief. Just, do you know intrinsic semiconductor? Okay, but let me, silicon, let's say, and also connect for silica. This is sharing first, this is also sharing electrons. So this type is also again this is pure. When we added 5 valency or 3 valency, pentavalent or trival, which is responsible for p and which is responsible for n type. How we can make the p type semiconductor in this intrinsic semiconductor? P type, n type, pentavalent. Okay, so please name, suggest one or two elements. Any name, arsenic, antimony, like that, phosphorus. And trivalent, okay, aluminum, indium. So okay, what will happen, let me just let me give you brief. Let me replace, there are 5 valence, 1 2 3 4, and one is remaining. Okay, one electron is also remain here. This is 5 valence. So when we mix 10 to the power 12 to 14 or around that much atom, doping, let's say donor or acceptor, so huge number of electrons are available. So majority charge carrier here, electron for p type or n type. This is n type, that's why electron n type. Similarly, let me replace with this, let's say arsenic, oh sorry, indium. 3 valency is there only, let's say one. I have also removed this. So 1 2 and 3, but one is remaining, needs one more electron here. So let's say this bond is break, then this will make here, so vacancy also here. So moving these vacancy holes, concept is hole here. This is p type. And majority charge carrier here also holes, and minority, some minority opposite, electron. Okay, similarly for n type. So please remember these things, just basic. And let's move for more advanced questions. This is next question. Okay, the region near the junction that is free for mobile charge carrier is called, the region near the junction that is free. Okay, let me admit. What is the question? The region near the junction that is free of mobile charge carrier is called. Okay, that is free of mobile charge carriers is called depletion region. There is no free charge carrier, mobile charge carriers. Do you know mobile or immobile charge carriers? Okay, we will discuss. Next question, the built-in potential in PN junction is due to external battery, diffusion of charge carriers or carriers, heating or illuminating. Diffusion. Okay, so then let me explain. You have P type semiconductor, let's say you have N type. Here is holes, majority is holes. Okay, and similarly, let me choose another color. Electrons, N type, majority charge carriers. Okay, and some holes and electrons, one or two may be found minority. What happened when we bring together or when we make the PN junction? What will be happen from near the contact point? These hole, let's say here is a higher potential, high number of charge carrier holes is too much that side, and almost zero that side. This is holes. So holes, there is a concentration difference. Okay, this side is too much holes, so and N side is less number of holes as compared to negligible, zero or almost. So there is a concentration gradient. Concentration gradient. So due to this gradient, like water flow high to, let's say water is fill here like that, and we have, let's say, hole here, so water flow. Similarly, due to gradient, hole wants to go the other side. When we bring together contact, at the contact, holes like move wants to like that. So holes recombine with electrons. Okay, and electron also in other way. Also a electron is higher, number of electron is higher that side. Also electron gradient wants to move p side. Electron also move, recombine with holes. So what happened at the junction? Let me, please be focused here. if you have p-n junction knowledge, you will very easy for semiconductor. So holes is recombined from that side. Initially that was the window. Hole is gaib, electron is combined. So hole is gaib, then which charge will be appear? Initially semiconductor is neutral, charge is neutral, atom is neutral, but hole is recombined with electron, hole is gone, then minus charge immobile, atom will, let's say we have atom, some silicon or something else, or electron is gained, so minus charge will appear on then that atom. Okay, similarly and n side what will happen? Electron is leave from here, so whole atom will positively charged. With my pencil. Just 1 minute, pencil is not working. Oh, discharge. So can you tell me what will be the, due to the minus plus, plus is n side, minus immobile charge carrier, also these are the immobile because atom is bound and charge on atom which is immobile, cannot movable, can't move. That's why we call these immobile charge carrier in depletion region. So plus and minus, due to the concentration of plus and minus, there is a electric field, built-in electric field. Direction will be, what will be the direction? Do you know? Higher potential to lower potential side. Okay, you can say like P to N or N to P. Okay, maybe charged. Okay. So electric field always put higher potential is P or positive charge and negatives. So positive to negative. This is electric field direction, built-in electric field. You know, electric field, what will be the electric field? This is the electric field formula, Coulombic force. There is a charge Q, or charge, summation of charge, total charge constant by R square, depend like that. So wherever is charge, let's say Q naught, have electric fields. Okay, R square dependency 1 upon electric field, any charge as associated quantity which is called as electric field. So due to charge positive and negative, electric field is developed at the junction. This is sorry, this is has junction, p-n junction, or depletion region, or space charge limited current called also. So electric field always positive to negative. Clear? this your point. 1 minute, let me read. Recombine at that region near junction from the mobile charge carrier leading to the built-in potential. Yes, so wait, I am coming to your point. Let me take another. To explain this, this is basic way. Okay, so we are initially holes, too much holes behave and let's say other color electrons. Okay, then next, these electron holes recombine. So first they recombine near the junction. Initially built-in electric field will be 0. Then let's say one electron go p side and recombine with holes, so they form this side is holes negative and this side is positive. So initially electric field is weak and gradient is too higher, so holes wants to move this side, holes, and similarly electrons also wants to move this side because there is gradient. This is hole gradient, this is electron concentration gradient. But initially will happen very fast. This is negative, this is positive, negative, and positive, negative, positive. Initially junction is not in equilibrium. Okay, so electric field after every recombination electric field become stronger and stronger. So at the point electric field has direction and to p electric field, and let's say focus one electron, or you can choose hole, whatever you want. Which color? Let's this electron now wants to move further, but now electric field is as much stronger, can stop this electron. How? Because electric field is n to p and also electron wants to go n side to p side, but this electric field electron feel force opposite in direction electric field. Okay, electron can't, if electric field force is equal to the potential gradient force, these two forces are equal, gradient force, this is electric force due to built-in electric field, they are equal, then diffusion will stop. This is called diffusion due to the potential gradient, due to the concentration gradient, sorry, number of charge carrier. So initially diffusion will start and develop the electric field will getting increase and much more stronger. At some point they are in equal opposite in direction, will stop these diffusion. This point is known as equilibrium point. Okay, without biasing. So this is electric field, and due to electric field, potential, built-in potential also develop. Okay, so let me give you just wait. Initially, holes, you have too much holes. If there is nothing holes wants to move. This is due to the gradient of number of holes is higher p side and very less n side, or negligible. So this is called diffusion due to the gradient potential, due to the concentration gradient of holes. Clear this point? Now similarly also for electron, they also wants to go p side. Okay, so at the junction they can recombine, electron and holes opposite in charge, they can recombine. And these charges develop n side and p side. Add to clear? Up to that point is clear? Now junction is formed. This side is negative charge and this side is positive charge. This is n type, this is p. Okay, here is electric field, positive to negative, always electric field positive to negative direction will always. Okay, this is built-in electric field due to these charge carrier. Okay, and this electric field also responsible for built-in potential VBI. What will be the formula in term of electric field? Do you know formula potential and electric field? Please remember small things. Not sure. Okay, very good. Anybody? Okay, P बराबर QE, or just we can replace like that, E by Q. Yes, you are correct. So this is whenever we have integration point like that, E by Q, and which is position dependent, dx dq dx summation over potential, just not dx. So we are here. Okay, so we are here. Built-in potential due to the electric field also. Charge is there, then always electric field also will be responsible for potential. Okay, charge associate, charge has, if charge is there always electric field or also potential due to the charge, available charge. Okay, so we are junction. So let me give you one more things. So every semiconductor you have valence band and conduction band. Okay, and one is probability function which is called Fermi level, intrinsic Fermi level, let's say EF. This is probability function of or chemical potential, we can say, of the electrons associate with electrons or also associate with charge carriers. So this is, let's say, intrinsic, pure. What will N type and P type? P type Fermi level will be closer to this Fermi level goes down closer to valence band because number of holes is higher in valence band. And this is Fermi level 4 N type EF, and this is Fermi level 4 P type. Let's say P goes up and goes down. Okay, then when we, this is P, let's say we have Fermi level for P, EF, P, and we have N type, let's say this is N. So when we keep in touch, like we have discussed, P and N at the junction, holes and electron recombine and they make the PN junction. So number of charge carrier redistribute. Due to these charge carrier redistribution and achieve equilibrium, when if we, let's say we have a different Fermi function, this is known also chemical potential of P type or N type. When we keep in touch, the chemical potential get in such like that only one Fermi level will exist at the equilibrium. So this is the entire Fermi level now for at equilibrium. Okay, at equilibrium only one Fermi level will exist. So due to this charge carrier redistribution and due to charge carrier redistribution, electric field also develop. Due to electric field also potential gradient, and this is cause the band bending. Initially how the P or N type move up and down when the material are connected, band bending. What is your point? Let me explain this, then we'll discuss your point. Okay. Okay, we will discuss, but first we'll focus here. So this is p type and n type, p type and n type. When we make the p-n junction, keep in touch, and holes and electrons are transfer, and these Fermi level align at same position, n type and p type, and here is the junction. This is, here is a band bending, conduction band, sorry, valence band also band for n type, and p type also for conduction band. Okay, why this? Because of redistribution of charge carrier and electric, due to this electric field is developed. Electric field also potential, this is built-in potential, this is that much, and this is cause the band bending. Okay, so okay. So first, you know, chemical number of charge carrier, holes and electrons. Holes is higher in p type, let's say. So Fermi level move closer to the this is tells us responsible or distribute, tells us distribution of the charge carrier Fermi level. So which side is higher goes to that side. So this is for p type, and n type, let's say here goes upside like that, n type, because number of electrons is higher in the coming in the valence band side. Let's say electron is n has so many electrons. Okay, when we keep in touch, they form this depletion region. Clear up to that point? Okay, now keep in touch. What will happen? Think yourself first. Okay, we have here guys, give me the answer this question now. We have discussed the direction of the built-in electric field in p-n junction. Now clear? B. Okay, very good. Let's see the next question. The majority carriers in n-type semiconductor. Okay, see, good. N means, let's say, electron. This is repeatable question. Okay, let me make like that. P type semiconductor, majority. Now, okay, holes. So this is 4n type. So answer will be A. Which device is based on PN junction? These are the four options: transformer, diode, inductor, or capacitor. Only diode. And diode is made by PN type material, PN junction, which is based on the PN junction. And characteristic we will discuss. Current, this is IV diode current. Okay, we will discuss this PN diode. Which device is best? Oh, multiple is, this is again and again. Sorry for this. Next question. Under forward bias, the current in a PN junction is mainly due to majority carrier, minority carriers, ions, or photons. Okay, let me give more. You have P and N, and let's say this is minus minus. We have discussed these things. How we connect: P is connected positive terminal, N is connected negative terminal. Okay, let's say we have some applied battery potential VA, and here is we have also built-in potential, you know. Give me that much is built-in potential VBI. So we have here VBI, built-in potential. What will happen when we connected P terminal to positive, and this is N? What will happen? You know, majority is holes, here is electron. Further, initially they are in without biasing, PN junction is formed, and our PN diode or PN whatever is a P type or N type and junction will in equilibrium. Now we wants to configure like that forward bias. What will happen? Now further we have applied potential, battery potential give to this. We have energy. These holes, or again electric field, built-in electric field, or this is electric field due to charge carrier, this depletion charge carrier oppose the further diffusion, but now these holes get energy or force due to this battery potential, again diffuse. Okay, again gets some extra force, extra force, they can over built-in electric field and diffuse. Due to this, current is flow, and which is due to majority charge carrier. Okay, and what will happen in this case? Depletion width is decreases, and built-in electric field effective built-in, this is V effective, also reduces. This is like that. Okay, built-in potential also decreases due to the external field, external battery potential. So give me the answer this question I have discussed with you. When a PN junction is forward bias, what will happen? Depletion width decrease, increase, no changes occurs, junction break. Yes, please give me answer all. Junction width is, this width is decreases, get the external force. Okay, so check your answer. B is correct answer here. So let me discuss. This is forward bias. Reverse bias, what will happen with reverse bias? We have question next. V effective at the junction, P and N. Now we have connected negative terminal to P side and positive terminal to N side. Please think, let's say initially VBI, we have potential VY, we apply VA, applied potential VA. What will happen? Potential, effective potential now at junction, VBI and VA, plus or minus, which sign is according to you? And depletion width, as we discussed, for the forward we have already discussed. Let's say W initially as W naught. Yes, please. What will happen here? Which charge carrier is flow? Which side to which side? Give me 1 minute. Sorry. Think. Electric field positive to negative. Okay, this is electric field, built-in electric field and also same positive support from outside. So this field is get higher and potential also get higher, so will be only plus signal. Okay, so barrier height will increase again. Now this we have initially let's say here. Now this is will be the initially VBI. Let this much difference is BA. Total is VBI plus BA. This is height, total height. Now electron wants to move at where get much needs that much energy, that much force or external. Okay, so please remember at junction effective potential get increased, depletion width also increase, V naught plus some effect due to the applied. Now will be that much. Okay, and due to this electron needs more energy, or when we eliminate the junction band gap is, let's say electrons fill barrier that much and behave like as a insulator, because there is no electron in conduction band. Furthermore, due to this reverse bias and ampere in microamp in reverse bias microamp, while in forward bias milliamp is a 10 to the power 3 order difference. Okay, sorry. So next question, and in an unbiased PN junction the Fermi level is unbiased PN junction, the Fermi level is, we have discussed this question. You have just PN junction unbiased. Let me give more. At equilibrium, yes please answer. Okay, 0. As we discuss, let's say we have like that. This is Fermi level now, AF. This is N side, this is P side. This is same throughout the all PN junction. Okay, so not 0, this is throughout the same at equilibrium point. Clear? See the next. Upon applying a forward bias in a PN junction, give me the answer now. Multiple choice question this is. One more option is correct here. Okay, other please give me the answer. So, as we discussed, upon applying the forward bias P injection, the whole diffusion current from P side to N side, number of holes is higher. Let's say P side, this is P, this is N, holes and holes, electrons. Hole further gets some external force and diffuse. Similarly, electron also get energy diffuse from N side to P side. Clear this point? Electron also negative. They also this feel repulsive force, and this is positive. They also feel repulsive force. Any doubt? Okay, next question. You have hint here also for this question. What will happen to the width depletion region upon heavily doped N side a diode? Let's say you have PN diode, PN, and N side is heavily doped, too much plus means more too much heavily concentration is, let's say we have 14, that size is 12 per centimeter cube charge carriers. Yes, please. Now let's say this electron is goes this side and recombine with hole. Other electron is, let's say hole is very less, let's say like that. So these electron recombine and recombine with this have too much recombine with also these holes, so recombine more P side. Okay, but only that much accessible area, let's say only that much electron is sufficient to recombine P side more area. Now think, give me the answer. Here is the density is too high N side, number of electron is too high, p side is too less. So exposed area will be high in p side. Am I right? Okay. So according to depletion width decreases n side and increases p side. Okay. This side is only few up to few nanometer or say accessible electron get diffused under too much. This side is higher than that side. This is, let's say, 10 nanometer, will diffuse up to, let's say, 50. So this type phenomena will happen here when we heavily dope. Or charge neutrality required always. These are the density of charge carrier and depletion width. So when we increase n side doping, what will happen? N is, we added 5 number of more electrons, pentavalent donor. So we increase donor and remain as constant. So this width should be decreases, only will balance this equation. If one is increase, second will be decrease in multiple case, if they are in multiply case, like here charge neutrality. Okay. Okay, see the next question. For an unbiased PN junction diode at thermal equilibrium, we have already at equilibrium. Which of the following statement is true? R is J, total is total current, J and drift, electron diffusion and drift. This is diffusion and drift current also. Okay, hole and both for electron and holes. So here have 4 option. At equilibrium, what will happen? Diffusion will occur initially. Let's say hole and electron. Electron diffuse and make this depletion layer, and first is diffusion current. Let's say some charge carrier, let's say from here minority charge carrier, due to the thermal fluctuation, electron hole pair are, let's say, make here. So electron get drift. This is called drift current. Okay, let me drift current due to electric field, built-in electric field, let's say VBI, let's say due to EBBI. built-in electric field called drift current. For n or also for all. So at equilibrium, drift current also balance, diffusion current also balance, no flow of charge carriers. All current should be balanced. Nothing will happen inside the material at equilibrium. Oh, carrier concentration flow will stop. Or balance each other, let's say, in other words. So now please give me your response. Okay, so let diffusion current also balance, also drift current. Please think, multiple choice selection are possible here. Multiple option will correct here. Diffusion and drift. So your C, according to your N and P side, diffusion and drift will balance. Okay. Also, C, D option. Check your option now. Drift and diffusion current are balanced to each other at equilibrium point. Two current are there. One is diffusion, other is drift. Drift current due to the built-in electric field, diffusion due to the concentration gradient. They will balance to each other and at equilibrium point, or they are equal in amount. Okay, so according to the statement, first option, an electron diffusion current balance to drift. Let me explain one by one to you. Electron is diffuse, okay, due to this diffusion current, but due to built-in electric field inside here, let's say electron and holes are formed inside here, so this electron is force and goes in opposite direction like that. So this is and drift. Okay, so if they are balanced only on at equilibrium point, so they are in opposite in direction, so when we add these two currents should be zero, there is no flow. Diffusion or balance each other, drift will be zero. Similarly for holes also in same way. so you can replace for also P. Okay, A, diffusion and drift. D, clear. And what else? C, let's say check, see what is diffusion and diffusion. And diffusion will balance P holes. Okay, diffuse electrons and recombine with holes. This equation is due to this. Or let's say one hole goes this side, one electron comes this side, so hole and electron balance to each other, and there is now at the equilibrium no net flow, current will be zero. Clear this point? Should I move for next question? Shall we discuss next question? Any doubt? Okay, let's move. Okay, thank you for your response. Let's move for next question. Consider a unbiased PN junction diode in thermal equilibrium and under dark, no illumination. So totally at equilibrium. When forward bias voltage is applied, then what happened to Fermi level of N side? The Fermi level of P side is, while intrinsic semiconductor is EI. Okay, let me give you more no, dark and these are two different things. Under dark and other will be under light or illumination. Let me take your point. Under light, when we expose our PN junction with photons or sunlight, so this is H nu photons will fall on the junction while dark means no photons, no light, means no external photon will give to this our PN junction. Okay, so what will happen under light? This photon is getting the material. If the incident photon, let's say h nu, has energy, this is our band gap material, is higher than the band gap, electron excited come into the conduction band from valence band. Okay, so under light we will disturb our equilibrium. If light is there, we will disturb the equilibrium, because we disturb the number of charge carriers. Okay, but in the dark no disturbance of the charge carrier. Clear? Okay, thank you. So this is next question. Please think. You have unbiased, without biased, and consider equilibrium under dark. This is the case. We will apply later on. Intrinsic. This is Fermi level, intrinsic Fermi level. EI. This is without. We are talking. Consider the unbiased p-n junction diode under dark condition. This is the case first. Okay. Now, when forward bias voltage is applied, what will happen to Fermi level n side? Fermi level of p side is this, and n side also is. So forward bias, you have to apply. Consider you have p-n junction also. P and n, you have applied p positive and negative. Initially, this is the case, EI at equilibrium. Now we connected p positive and negative. What will happen? We again disturb these number of charge carrier, p side holes and n side electrons. We will disturb these because diffusion will happen further when we apply forward bias. Yes, am I right? Now please think, if, let me give one more thing. If let's say hole is decreases, let's say hole is decrease, Fermi level goes upside, slightly goes up. If hole is diffuse, hole is decreases. Similarly for electron, if electron is get less, Fermi level goes down. From conduction band to closer to mid gap in separate p and n semiconductor. But here is the case for p-n junction. Yes, please. What do you think? Answer. Please see the answer. A and B. Now check your concept. What will happen here? Fermi level of n side is higher than the Fermi level of p side. And other option B, Fermi level of n side is greater than also the intrinsic or under as a equilibrium. Wait, let me give more expose for this question, otherwise you will confuse. Please focus here. Initially you have one EI. Tilted. Let me make first Fermi level, then easy to make. This is P and this is intrinsic semiconductor. This is for equilibrium. Okay. Now what will happen when we connected this forward bias? All cis goes from here to N side, as we discussed earlier. Okay, and similarly electrons come to P side. Up to here clear to you? Up to clear? Now initially let's say this is intrinsic, this is for Fermi level for P type, and initially I'm talking with initial point Fermi level for N type. Okay, what will happen now? Equilibrium are disturbed. No one Fermi level is there. This condition is called quasi Fermi level, quasi state, because now and okay, they are not in same, some ups and downs, because we are disturb the equilibrium and not at the equilibrium point now. So this connection will no, let's say initially we have one Fermi level like that. Oh, this side is, wait, so when a holes is get less means goes upside. Clear? Fermi level goes upside. This is new case. And similarly for air, initially here electron is less means go down, and this, wait, not much level is not much, that level means here go, let's say this is new Fermi level and not are at the same levels, because our PN junction at not at equilibrium point. Clear up to that point? Separate Fermi level are built up when we applied the bias or illuminate with the sunlight, because we are disturb the charge carriers. So holes are getting diffused from p side to n side, and an electron also diffuse from n side to p side when forward bias is applied. Getting my point? Okay, thank you. So Fermi level, intrinsic Fermi level and other Fermi level, please check your options. And I have wait 1 moment. At disturbing point you have n and p. This is p, this is n. So this is Fermi level for p type, red, and p type in n side is very less, you know. Yes or no? P side, n side holes is very less. Fermi level, where will be the Fermi level? Above the mid bed, let's say here. And take another color. For n type, let's say here the case for this is Fermi level for electrons, and electron is very less in p side, you know, minority charge carrier. So will be like that. So different level are form. This is Fermi level for holes. Okay, so separate level are forms, and these gaps, this splitting gaps is equal to the applied potential. Okay, see, I think and check. Fermi level is just tell you about the concentration of charge carriers. According to the concentration of charge carrier will go up and down. Please search the quasi Fermi levels under for solar cells. What will happen in PN junction? Quasi Fermi levels. Splitting of the quasi Fermi levels give to the open circuit voltage of solar cell, which is essential in the solar cells. Okay, Forget about the question, please think about the concept. So please search and check your memory or whatever you learn. What will happen under illumination condition of p-n junction when we illuminate with sunlight? Next question, which of the following is valid reason for p-n junction diode is an unbiased dark condition? Please give me the answer. At equilibrium. This is simple question as we discussed. No furthermore charge carrier flow means neither generation nor recombination take place. Clear? When we reverse bias is applied p-n junction diode, it will this is simple question, please give me the answer. We will discuss this question in initial reverse bias. And reverse bias, let me wait, my pencil is not charged. Please think as we discuss in initially reverse and forward bias starting in the beginning today class. Guys, are you there? Okay, thank you for your response. In the reverse bias applied to p-n junction diode, pencil is not charged or what? Okay, so let's say you have p and n. Let me connect with its opposite. This is negative positive terminal. External field you have applied external potential VA. There is a built-in potential VBI and think like that. This is without biasing. When we this is the potential barrier, this is called the potential built-in potential VBI, which is field the electron this is this much barrier has to cross this level air to air, feel that much level, need that much energy or force, applied force. But when we applied VA, as we this level is getting more higher and higher like that. So this level is goes down much down because we effective potential VBI plus this VA, as we this is plus this is electric field is in this direction at the junction, you know, this is electric field and also support with positive So this field is get higher, so due to this potential will get higher, and that much amount Va. So this barrier goes more higher, so raise the potential barrier for the carrier transport. Okay, initially let's say here, and raise to up to here. This is, let's say, VBI initially, and this is VA. That is effective. Clear? And what will happen with charge carrier? Electron toward the n side due to the external field, and holes toward the p side due to the external field, or in other words, majority charge carrier in reverse bias get away from this junction. This point is clear to you? Because this side is hole, so this is negative, and holes will attract by this terminal, or pull by this applied external field, and electron also pulled by this. That's why this depletion lid is broader, broader. Now due to this applied Va. Clear? So let's move for next question. The electric field in the bulk region of PN junction under bias. Bulk. Where is the bulk? Let me give you. This is P, this is N, this is depletion region. And this is known as bulk region of P side, and also this side, bulk region. Open side. Okay, now give me the answer. Electric field in bulk region of the PN junction under biased is positive, negative, zero, or sinusoidal. So answer will be, because only one type charge carrier, no gradient. Only here negative, positive, and negative. So here is a electric field only in junction, only at the junction. In bulk, zero. Okay, next, see the next question. This is the question. Depletion region. Question is about charge density in the depletion region. In the depletion region on P side, PN junction. Okay, so you have P and N. P side, you know, negative charge. Am I right? And N side, positive, as we discussed initially. Why? This electron is leave from N side to and merge or recombine with holes. So leave atom, let's say we have silicon and also, so electron is released by these atom, and atom get plus charge, immobile plus charge. Okay, similarly for p, this side, whole side. So charge density at p side, this side, density means charge and number of charge carriers. So let's say q and n, and what is the sign of q, p side, please tell me, p side. Please see the sign, guys, please see the sign. Negative or positive? P side. Negative, thank you. As you can see in the picture, I have already written negative. So let's say q is small charge, and number of this q is electronic charge 1.6 10 to the power minus 19 coulomb will be. This is fundamental quantity. And if question asks n side, this is which option will be correct? Second. N side, now n side is positive charge plus q and number of charge carriers, whatever is acceptor or donor. Okay, according to. Clear this question? Next question. Which of the following statement is are correct for p-n junction diode under dark condition? Means at equilibrium. Give me the answer, please. Okay, B. Multiple selection will possible here. Choice will be correct here. As we discussed previous question, A is bulk inside 0 and depletion region is not 0. This is correct. And see the answer. B also, free charge carrier density within depletion region is 0, and in the depletion region this no charge carriers, no free charge carrier, means only mobile charge carrier, no free charge carrier. Charges. Okay. And is 0 this side and this side, but not 0 at the depletion, is not 0 here. Built-in electric field is there. Equal to 0. Okay, only electric field, if there is negative, positive, let's say have the electric field, but let's say you have atom silicon, number of electron and holes, negative and positive charge, in the atom, total number of electron equal to the total number of holes or proton electron, proton, neutron. Neutron, there is no charge, but electron has charge, you know, negative charge, and holes is proton has positive charge. So electric field due to proton, let's say q, number of proton equal to the, you know, n number of the charge carrier. So let's say kq by, this is electric field due to the protons equal to the k n negative charge of electrons by r square, will be the same. So basic point is there. So electron and holes are equally at the atom, and this side is neutral region, because atom already initially, when we make, let's say silicon, we have semiconductor, silicon, the atom at initially is neutral, means number of electrons are equal to the number of protons. Yes, am I right? And no net charge electron or holes, they are associated with their nuclei and surrounding by the flow of the electrons. So atom at initial is means no charge, net charge, electron and holes are equal, they cancel each other, means electric field due to charge, obviously there is electric field, but they are opposite in nature. Electron has negative, holes are, or proton are positives, they cancel each other field, so net field is 0. In the depletion region, the case is different, because these atoms get positive and negative, get charged. Due to this, built-in electric field are formed at the depletion region, but number of electron is coming from the n side equal to the recombination at p side will be the same, one electron recombined with one hole. So net left, net region, bulk region is without getting any charge, neutral region, or you can say every atom has number of electrons equal to the number of protons. So there will be no electric field, net no electric field. Clear? Okay, thank you. So yes, no electric field in the bulk, because bulk has neutral region, no charge, or electron or proton are same on every atoms, so no net charge density. Okay, or you can say, let's say k number of charge positive and negative by r square, they are in same quantity, let's say n, and opposite in sync, they are cancel each other 0, so electric field will be 0 mathematically. C option, what will be this? Current in the bulk region is determined by the diffusion of the majority charge carrier. Yes, please remind this point. And in the depletion region, minority charge is responsible for current, while in the bulk majority charge will responsible. Because in the depletion region there is no free charge carriers, only immobile. So when we illuminated via sunlight or anything, bonds are break, electron and holes are form. These are minority charge carriers and will take place in the current, like diffusion. Sorry, drift. Drift current associate with the external field only, and diffusion will associate with the concentration gradient. Okay, let's see the next question. A silicon based PN junction diode maintained at room temperature under equilibrium condition has a p side doping, that is the number, n side 10 to the power acceptor 13 is, and donor 10 to the power 16 per centimeter cube respectively. The value of built-in potential would be, we have to calculate built-in potential VBI, KT by Q ln ND plus Na upon NDNA. Please apply this formula and get your answer. Okay, you have to apply this formula, and you know donor and acceptor. So let me show you the solution, because we are running out of time almost, and many question is left. Okay, so please see the solution. This is the formula. Please remember this formula. Built-in potential KT by Q ln ND Na by Na square. Sorry, this is different. First I write. Okay, so Ni is also here. Ni is 10 to intrinsic area 10 to the power 10. ND and Na is already is given to you 10 to the power 16, 10 to the power 13 per centimeter cube. So please put this value in this equation, and KT by Q at room temperature of 300 will be KT 0.026 electron volt, and also is Q electronic charge, E is cancel out, this is in voltage, volt only. So this is unitless quantity will be in volt. Clear this solution? You have to just apply the formula KT by Q ln ND Na by Ni square, and just use calculator and please calculate. Should I move? Let's move for next question. This is the question, which of the following is correct Einstein relation? Please remember, electron is non-degenerate, non-uniform semiconductor. So Einstein relation always will apply whatever the semiconductor. Okay, so please remember this also, the relation, diffusion, movability and KT by Q. Next question. A homojunction diode is under forward bias condition with applied voltage 0.3, given doping concentration on both P and N side is diode is 10 to the power 15 and intrinsic area 10 to the power 10 at 300 Kelvin. What will be the junction potential? So under forward bias, so you have to calculate V effective. You have to first we have to calculate V built-in potential. Then what will happen in under forward will be minus V applied. You have V applied 0.3, and VBI we can calculate as we earlier calculate KT by Q ln what is NdNa by Ni square. Please use this formula and use this concept. First you have to calculate VBI, put here VBI. Clear this concept? I will show you the answer. Please see. First we will calculate the Kt by Q, Ln. These are the numbers. We have put both side 15, 10 to the power and intrinsic 10 to the power 10. So this is built-in electric field. So nu is here is applied. So this is the concept. Under forward potential barrier will reduce. So whatever we applied will get minus. Okay, so 0.3 will minus, get your number. D will be the answer. Okay, next question. The diffusion coefficient of electron and holes are given. Respective carrier lifetime of electron and holes also given to you. The ratio of the diffusion length d and tau. This is the formula. Diffusion coefficient with diffusion carrier lifetime. So both are given. You have to take just ratio. So please see. We have applied the for electron and holes and take the ratio and put these number 50 and 25 we have put already, and carrier lifetime tau, these numbers you will get 0.4. Okay, next question. Consider P and N silicon, P type and N type. Fermi level you have. Which of the following is true? Thermal equilibrium when both them are joined together. At equilibrium Fermi level will same, okay, throughout the at equilibrium. Next question. This will be, I think, one more question. A silicon PN junction diode, P type region containing acceptor and region donors. What will be the total width of the depletion region? Applied voltage 0.4. So let's see the answer. You have to, this is the formula for potential for depletion width. So this is the formula, and we have to also calculate the VBI. VBI, you know, Kt by Q. We will apply Kt by Q. Just put the number and other things already given in the question. And as I calculate VBI, first I calculate VBI, I will get this number and put here this number, and applied voltage also given you, and donor acceptor you will put here, and this is permittivity and space permittivity, relative permittivity and space relativity. This is case not. So as I put here numbers and just use the calculator, you will get the depletion width. So please remember this formula if asked. So this is the last question for today. Which of the following represent the ideal diode equation, PN junction diode equation? So this is the answer, diode equation. Please remember this equation, and this is give to you this V and I. Okay, why V is applied potential, whatever we applied on the junction. whatever we applied. This is just equation applied potential. You have to put just number. We will solve this equation, or we will discuss next in assignment. Okay, question on bed this. Okay, thank you. Please join next meeting on Monday, next Monday. If you have any doubt, please ask then. Okay, thank you for your interaction, live session. Let me end the session.